Hello everyone, and welcome to the next chapter, chapter 4 of the MI205 class. We'll follow the same kind of structure that we've been following in the last classes. I'll stop along the way actually asking for questions, but if you have any, just type them along the way in the questions box and I'll answer them as I get them. Today what we're going to cover are data summaries. So hopefully by the time you complete this chapter and the homework, you'll be able to prepare our object for summarizing, generate some simple frequency tables using factors that may or may be present in the data set, understand the usage, at least in the simple case, of the apply, lapply, tapply, and aggregate functions, and then finally subset data frames using a logical vector. And as in the past, we may or may not complete all of the material in the lecture today. If we don't, we'll finish it up on Friday. Okay, and for those of you, if you want, you can follow along in the PDF. I'm not going to broadcast it. Just have up the our interface, and I'll be typing some commands in there. So we talked a little bit about importing data before and getting a handle with some really basic functions in R, things like mean and median. But what's sometimes difficult to do with some of those standard functions are really see what's happening at either the individual level of a variable, say what might be the maximum concentration within a patient, or maybe at the intersection of two or more variables. So let's start off by just loading a quick data set here. We don't actually need the Metrum RG package of functions this time, but it's loaded anyway just so you can see it. I've supplied a prob1.tab data file that we'll be using today for the class. So what we're going to do, first thing we're going to do is read that in. So if we read that in, we can take a look at it, do something like head prob1. Oops. Sorry about that. Now you should start seeing my screen. Thank you for pointing that out to me. Sometimes I get a little ahead of myself here. Okay, so where were we? Okay, we were loading a data set. So I did was, now that you can see my screen, it'll make more sense. I've loaded the prob1 data set. And I've supplied you with that, and if you look at it, we took a quick look at the first 6 lines, and if you remember, head is something that allows us to look at the first couple of lines of an R object. We can see that it has things like ID, which is an identifier for patients, dependent variable, amount, time, and some covariates, things like height and weight and creatinine clearance. And if we want to know, say, what's the median dependent variable, what's the median concentration? This is a concentration data set. We could type something like median prob1 dV. And that'll give us the actual median of the dependent variable. Or we could do something like mean. And these are all summaries. And again, we can do that. And we've actually even solved the use of the function summary from the first week. And let's say that we wanted to find out, in this case, I believe, this data set, we have a factor variable, sex. I believe it's 0s for females and 1 for males. So let's say we wanted to know what the summary of the concentrations in females. We could do something like the following on the command line. We could use the summary function, and we could subset on the fly to sex equals 0 and simply the DV column. And if we did that, we could get some nice summary statistics. For everybody who has a sex of 0, we could find out what their minimum, median, min, max. And that's all fine and well. That's very nice. And for that matter, we could even just do a summary on the whole data set. And now you can see a very nice kind of general summary across all the variables, things like min, median, max, maximum. If there was any NA values, it would actually tell you that as well, and we'll see that later on in the course in this class. And though this is very, very nice for kind of getting very quick summaries, it gets very, very hard to kind of do this at the individual level. You know, you could also do something like this. You could say, let's say you wanted to get a summary of concentrations for ID equal to 1. You could do that, and then you could do this for every individual in the data set, which I believe goes from 1 to 40. And you'd be here typing for quite a long time, and you'd get information back to your screen, but it's not very usable. So what we want to do is we want to start taking a look at some functions that will allow us to do some of these summaries in very few keystrokes, and in some cases save them out to another R objects for plotting or for use in other calculations. So in order to do this, I'm going to make the prob1 data set isn't all that interesting, so I'm going to make it just a little bit more interesting. And just to keep in mind, as you're moving through this experiment or you're moving through this particular week's course when you're finished here in class, if for some reason you do something to prob1 that results in, you know, messing up with the columns or messing up with the data set in some way, you can always just read it back in again. I've supplied it to you. So at any time, you can just read that prob1 data set back in again using the read file command. So what I'm going to do first is, I supplied to you also, there's a script called for.r that basically encompasses all the commands. I'm not going to step through what you see up here on the screen, but just suffice to say that what we want to do is we want to make it a bit more interesting. So we're going to do a few things into the prob1 data set. We're going to generate some additional columns, some columns for different races, some columns for maybe food categories, maybe fed, fasted, or unknown. We're going to generate some weights. And we're going to do this in such a way so that I'm setting a seed up here so the things that are based upon generating random numbers are reproducible, so I can always get the same result. So I'm going to do that first. So let's go ahead and run through some of these. And some of these functions you're going to find out later on. I think in the weeks to come, you're going to learn about functions like merge and probably sample and R norm. But for right now, we're just going to take it on face value that they're doing what I want. And basically, I'm merging some of these data that I've created back into the prob1 data set. So if we take a look at what prob1 looks like now with the head function, what we're going to see now is we have some additional columns. I've added race, food, and a second weight column, or I should say a weight 2 column that I just generated that has a mean of 5 and a standard deviation of 2. Now what I'm going to do is I'm going to further create some columns. I'm going to add weight and weight 2, then I'm going to create another column called weight 3, and then I'm going to fill in some values for weight 3 just so we have some NAs in there. And then I'm going to factorize race, sex, and food, and that's so that we can look at, that's so the summary function is a bit more informative. Because if you remember, let's go back just real quick, it's worth spending just a second here. If we take a look at summary of prob1, remember, I've added some additional columns, but if we look back at these, some of the summaries of some of these columns really don't mean a whole lot. For example, you calculate summary statistics on something like sex, which is really a 0-1 variable, and it's giving you things like the median value and the mean and what the max is, and we already know it only goes to 0 and 1. So by factorizing it up here, summary will treat it a little bit differently. It'll treat it as a factor because it knows that it's a factor. And so it'll give you other statistics. So let me go ahead and generate these other columns. And we'll take now a look at summary prob1, and what we'll see here is now for things like sex, now that it's a factor and summary recognizes it as a factor and R knows that it's a factor, it calculates something different. So instead of giving you things like min and median and max, it just starts to give you the total number per category. So in this case, it says you have 345 rows that are sex equals 0 and 255 that are sex equals 1. And you can see the same thing down here with race and food. Now again, these may or may not be all that informative depending upon what information it is you want to get. By that I mean, if you really want to know how many males and females you have, this particular summary doesn't really tell you. It really just tells you how many rows contain zeros and ones. So let's go on to the next step. And the first thing we're going to do is let's take a look at the function called table. And table simply generates a frequency table of the counts at each combination of, say, a given factor level. So for example, that's probably easiest to explain it. Let's do something like this. Table prob1 $sex. So now what we see is it's very similar to what we saw in the summary. In fact, it's exactly the same as what it did up here in the summary line. But now it's a simple one-item summary with a very concise method to get there. Table prob1 $sex. The nice thing about table is you could see how two different variables interact. So you could do something like table prob1 $sex, comma, prob1 $race. And so now what it does is it still gives you the 0, 1 for sex, but now it further breaks it down by race. So for sex equals 0, you have 105 African American rows, 90 Asians, 75 Caucasians, 75 other. And for the sex equals 1, the items are listed there as well. Now you could break that down even further. Or what we could do is, this is not really as informative as it could be. It could be more informative what we see here now is we know that there are 345 zeros and 255, I should say, rows that contain 1 or 0. So, but what we really want to know is we want to know how many individual males and females there might be. So one of the things we can do really on the fly, we can go ahead and use the subset operator and the duplicated function. So what we would do is and wrap all that in a table step. So if we do something like this, table, and we say prob1, now we're going to use the subset operator and we're going to say, okay, what I want is I want only the unique rows of ID, so I want to say bang duplicated or not duplicated. I can't think of the name. That symbol before duplicated is bang duplicated, I should say, is going to give you individual IDs rather than say give you all the rows. And then we could say, now we have to supply it some columns, so we could say sex. So now what it's going to give me is, now it's going to tell me exactly, exclamation point, yeah, sorry, thank you, one of the students there. I drew a blank there for a second as to what that was. So now we have females here that are 23 and we have males that are 17, or these could very easily be 23 males and 17 females. It really doesn't matter, but what the key thing is here now is, now we actually have know a true level of how many there are. And you can then further add additional columns here. Okay, so we could say race. So now what we've done, just to rehash this, we've wrapped everything in a table, the table function, and we're operating on the prob1 data set. We're okay. Just give me unique IDs, so it'll give me only the rows that have unique IDs, and it's going to give me the table based upon sex and race. So if I do that, now again, we have a bit more some more informative information, at least from the way I would look at it. So now we know that those 23 individuals are separated by 7 African Americans, 6 Asians, 5 Caucasians, and 5 other, and then the males would be 7, 3, 5, and 2. So it's a bit more informative information. And you can take that additionally one step further, and we could say something like this. So now, let me make this a little bit bigger so we can see everything on the screen, hopefully. So now what we've done is we said, okay, tell me give me the interaction of all 3 variables. So okay, when food is 0, how many males and females do I have? When food is 1, how many males and females and races? And when food is 2, how many males and females and races? Now, so what is this going to help you do? Well, first of all, using the duplicated along with the table, it gives you more informative information. So now you actually know what cells you have data in and what cells you don't. So for example, with food equals 1, we know that there's no information in this data set. There's no people that are also have a race of Caucasian. And we know, for example, that if food equals 0 and sex equals 1, we have none of the other race, whatever that catch-all is. So what might that help us do? Well, it's going to help us maybe it'll help us make some general decisions. So maybe you'd want to do something like this before you started working with the data set, before you started an analysis or something like that, to say, okay, well, do I have enough information to answer questions like, maybe what are the effects of gender on clearance? Do I have enough males and females? Yeah, I would argue that you might, depending upon what your model is, but those kinds of questions. Or maybe do I have enough information to estimate the effects of food? In this case, I have food 0 is fasted, food 1 is fed, and food 2 is unknown. So how many do I have of those different categories? And then finally, can I answer questions like, what are the effects of food given gender? So, if I have the different food categories, can I tease out effects of food and gender? So again, whether or not the questions are something that you can answer necessarily with whatever analysis you're doing, this one particular summary will at least give you some idea of the cells that have information versus the cells that don't. Okay, so what I'm going to do actually is what we're going to do is I'm going to go back to the exercises. Either I'll let them up to you to do for homework, or we'll go back and cover the exercises once we get through the material today. So what we're going to do is we're going to jump right into another set of functions really that kind of is more complex than table. And these are the apply family. These are the interrelated functions: apply, t-apply, l-apply, and aggregate. And these do exactly what they sound like. They apply a function to a given R object. So the first thing we can do, you might say, well, what do I need to supply? What arguments do I need to supply to a given function? Well, we could do something like args apply. And that'll tell us that function takes at least 3 arguments. It takes x, it takes margin, and it takes fun. Now, that still may not tell you what exactly it is that that function needs. So you could do something like question mark apply. And what that'll do is that'll actually open up in your little help window off to the right. That'll actually open up the actual help. And then with this window, you can start to see more information about what it is. Okay, well, X is the array or the data that's going to be used. Margin indicates whether you're going to apply the function over rows, if you set margin equal 1, or 2 indicates columns. And then function is actually the function you're going to apply. And you can go on through the details and learn a little bit more about those. But for our sake, we kind of have enough information at least to move forward with where we want to be today. Okay, so I'm going to borrow from my little R script up here so I don't have to type all this out. Let's go ahead and run a simple apply. And I'll copy it down to the screen, then we'll talk about what it is we're doing here. Okay, so what are we going to do? We're going to see this theme actually throughout the day today. The function we're going to running is apply. We're going to specify what the x values are. So in this case, again, we're on the fly, we're subsetting the data set. And you could do this up front if you wanted. You could create a new data set that has just 1 row per individual to make this a little bit easier. So you don't have to type all this on the fly. But we're subsetting basically so that we have 2 columns that we're going to work with: weight, and in this case, crat and clearance. and we're setting margin equals 2 because we're going to be working with columns, and the function we're going to be applying is mean. So what we could do is we can go ahead and apply that function. And so what did it do? Well, first of all, I subsetted the data so it was one line per individual. Then I applied the function mean across those two columns that were available. So what did it tell me? Well, it tells me across all the individuals what's the average weight and what's the mean weight and the mean creatinine clearance. You could apply a function as median, it can be whatever function that you would like to some degree to apply. The other thing we could have done here, let me just use the up arrow feature. Now, instead of applying it across columns, let's apply it across rows. So now what we're going to do is we're going to work with the same exact subset of my data, weight and creatinine clearance, but we're going to apply the function across the rows of the data set rather than the two columns. It's going to give you something a little bit different. So now what I've done is I've gotten what amounts to what it amounts to is the mean value for weight and creatinine clearance for each individual. But if you remember, each of these individuals have only one row. So it's really just the first row value for each individual. But now what you'll notice is we have, count this, I believe we have 40. We should have 40 answers here. So we have one value for each row. Actually, what it did is I'm sorry, I take that back. What actually we did here is we individualized it so there was one row per individual, and then we took the mean across the rows. So we meaned actually weight and creatinine clearance together, which really doesn't mean a whole lot. But let's do this instead. Instead of using weight and creatinine clearance, let's do weight and weight 2. It makes a little bit more sense. And so now what we did is we took, if you can imagine that each individual has two measurements of weight, we could say, and we averaged those two together across the rows. So we have two columns, and we took row 1 and we took the average weight, and we took row 2. So it's basically a weight per individual. Again, I'm not so sure how informative it is, but one of the things that you could do, let's say that you wanted to something that you could do relatively easily that we couldn't have done using something like summary. We can write this information to a file and then use it later on to do some plotting. So let's do this. Let's take the same basically the same apply that we did, but we're going to write it to a file this time. So instead of seeing it out on our screen, we have a file called weight.ind, case sensitive. And now we see the same results again. But we can use this as part of plotting, and Jim has initially talked with some plotting, so we'll just use the base graphics plotting here, nothing too fancy. So what we're going to do is we're going to plot for each ID, we're going to plot the value that corresponds to weight.individual and the X labels ID and the Y labels mean weight across occasions. And we're assuming that occasion 1 is weight and occasion 2 is weight 2. It's in this case, it's not critical, but so what we can see here is a nice little plot of mean weight across occasions for each individual. And we have 40 dots on here and one for each individual. So that's one nice piece of using the apply functions and writing it to a file that you couldn't have very easily gotten using the summary function. You couldn't have gotten to those numbers very easily. Yeah, and actually somebody asked us a question. Does function, if you'll notice in my function arguments, I've used the mean function, or we could have used median. You could also have written a function. I'm not going to do that, but Tim had talked to you a little bit last week about writing functions, and you could have supplied your own user-written function. We could have defined a function previously to running this apply command, and then past that function that we created here in the function. So it doesn't just use our built-in functions, it can use a function that you would have created as well. Okay, so that's apply. That's kind of the simplest or one of the easiest apply functions. Now let's take a look at some of the variants of apply. The next one we'll look at is lapply. And again, if we don't know what arguments lapply takes, we could say args lapply. And I have to spell it right in order for me to figure out what they are. And now you'll notice that there's only two, it only takes two arguments, x and function. So in this case, what it does is it applies the function against each element of x and returns a list the same length as x. So what that means is this function operates only on columns of x. So what it's expecting is a set of columns or one column to be passed into it. So let's see how this works. That's probably the easiest thing to do. And for my purposes, so I don't have to keep writing the bang duplicated step here, we'll go ahead and we'll create a new data set called prob1.ind. Nothing unique about that name. I'd have called it whatever I wanted, but that lets me know that what prob1.ind is. For my shorthand note, it just lets me know that that has individual level data. So it has one line per individual. And how do we do that? Well, we just said bang duplicated on ID. And if we do head on prob1, what we'll notice here is that we only have one line per individual, and we could do nrow prob1. Actually, we could do nrow prob1.ind. I had calculated the number of rows in the total prob1, which was 600. Now the number of rows in prob1.ind is 40 because there's one per individual. So now we can go ahead and use that lapply function. And let's go ahead and get an example of that. So now what we did is let's use the max function across the columns dv and weight. So what we're doing is we're saying, what's the maximum value in each of these columns? And weight 96 seems reasonable. That these are measured on typically a patient's weight. Maybe this is their baseline weight. Of course, DV maybe doesn't make a lot of sense because we know this is a concentration data set. The maximum value of DV, in this case concentration, is 0. Well, I guess it does make sense when you think about what we did to this data set before we actually ran this function. We actually limited this data set to one line per individual. Then we calculated the maximum. So actually, DV, since it's the first line for individual, it's going to be 0. So we got exactly what we wanted, but maybe it's not. We got exactly what R gave us the right thing, but maybe it's not exactly what we wanted. Let's try a different approach here. Now what we've done is we've used lapply across the entire data set. Across the prob1 data set, and we said, okay, what's the maximum DV and weight in that data set? And again, the maximum weight shouldn't be surprising because, that value is the same as it was before, simply because we had one line per individual and weight was continuous within an individual, so it's still going to be the maximum. What's going to be different, though, now is DV. Now we have the true maximum DV value because we use the entire data set. So let's take a quick look at problem 1, just so we know what the difference here. Problem 1 is the original data with 600 rows, so it has everybody and all their observations in it. Prob1 IND had just one line per individual. Let me just show you what prob1.ind looks like. So now very nicely you can see here the difference mainly being between these two is that the IND one has only one line per individual and prob1 has all of the rows for all the individuals. Now, let's try this lapply on a different column. Let's try it on this weight 3 column. So now we have the same result again for dV because we're just saying what's the maximum value for dV across this prob1 data set. But now for weight 3, what you'll notice is it's giving you back the value of Na. Mainly that's because there's at least one Na value in that weight 3 data set. So the function max, by default, if there's an Na in there, it's going to give you back Na as the result. Now, you can get around that, and if we do something like args max, what you'll notice right away is one of the options for maximum is na.rm. And what that means is that remove Na values. By default, it's set to false. We could have simply set that to true and done something like the following. And now we have actually the true maximum after it tosses away all the Na values. So one of the things to take home here, one of the methods here to remember is when you string these, when you make the lapply command, right after the function argument, it'll be obvious, depending upon whatever function you supply here, there may be other arguments to that function that it'll take. And so what you can do is just string them along afterwards. So in this case, the function was maximum. The additional option is na.rm, and I can specify na.rm equals true. Okay, so let's take a step back here just for a moment. Somebody's asking here, now's a good time as any, to how margin equals 1 works. So we did this within the apply, and so when I talk about apply, margin equals 1 says apply the function across the rows. And probably the easiest thing, let's take a look at prob1.ind. So prob1.ind, this is the prob1.ind data set. Now, if I wanted to find out what the average weight was for individual 1 using weight and weight 2, I could apply this the function mean with margin equals 1. So for example, I could do something like this. And I'll explain these as soon as I type this together here. So now what am I doing? Okay, I'm taking the apply, and this is a subtle point, but worth understanding. I'm taking apply, and I'm going to apply it across margin equal 1, so I'm going to apply it across the rows. So it's going to say, what's the mean of, for row 1, what's the mean of weight and weight 2? And it's going to do that for every row. Actually, what I did was I said weight and weight 3. What I wanted to say was weight and weight 2. So it's going to do that for every row. So now it says, okay, let's take the average of 91 and 98, take the average of 47 and 54, and it's going to, that's basically when you say margin equals 1. And now for the difference is if you say margin equals 2, instead of getting 40 answers, we're just going to get 2 because it's going to actually use columns. So it's going to say what's the average weight down the column of weight and what's the average weight for the weight 2 column. Again, both useful, but both telling you different things. One tells you the average weight within a patient, and that's what we plotted. And the other one tells you the average weight for a given column. And weight 2 is just a variable that I generated. There's nothing unique about it. It's just, let's just consider it the weight on the second occasion. We'll just call it that. Has no other meaning. It's just something that I generated to use as statistics today, something I could use in the data set. So you can think of this as weight on the first occasion, weight on the second occasion, weight on the third occasion. May or may not do this, organize it this way in a given data set you've dealt with, but that's what we've done for this one. So that's really what the weight 2 is. It's just a variable that we can use to do some summaries. One of the other things you'll notice when you say margin equals 1, it gives you the answer, like say 94, and it gives you the row that it was calculated from. So row 1, row 16, row 31, row 46. And if you look up here in prob1.ind, you'll notice the farthest column to the left are the row names or row numbers. Row 1, row 16, row 31. Because this is 16 is what it was in the original data frame. So we subsetted it, but that row name still came through. So this just identifies, these numbers at the top here, just identify the row that the function was applied across. Okay, so that's the apply and the lapply. Let's take a look at, and obviously you want to be careful when you use the lapply function, because you want to make sure that it's giving you exactly what you want. You know, in this case, we have to make sure that if we have NAs in there, that we definitely wanted to get rid of them. So let's take a look at the next variant, and that's tapply. And if we take the arguments of tapply, now there's a couple of new ones in there that we haven't seen before. One is X, that's typically, again, the data that you're dealing with. Index is the factor level, or the level really to apply the function across. Function, again, is just simply the function you're going to specify. In this case, it came with a null value, so if you don't specify a function, it'll be no function at all. And then there's an option which is simplify equals true, and we'll take a look at what simplify equals true does. So let's first of all, let's just take a simple look. Let's use tapply, and we're going to use it with our prob1 data frame. Remember, that's the prob1 data frame is where we have all the data from all the individuals. You could say the superset of data, all the information. So now what we're going to do is we're going to use tapply. We're going to apply it across the DV column. And the index we're going to use is ID, and we want to know the max. So what we're going to be doing with this is we're going to be calculating the maximum DV for each ID. And I wrote this out to a file called maxDV. So if we look at that now, what we see is now instead of having row numbers across the top, what we have are the levels of the variable of the index. So here I have an index of 1, 2, 3. These correspond to the ID value. And then listed below it is the actual maximum value for the dependent variable. So you'll see, again, 40 of these values. And you'll notice one of these has a value of 21.28, which was a maximum that we saw previously. Now, we can also supply the simplify argument now. By default, simplify equals true. So it just simply gives you back a vector of numbers that correspond to the ID with the result. The other thing we could do is we could say simplify equals false. Now let's take a look at what maxDV gives you. Now it gives you, rather than a vector of results, it gives you a list. And each element of the list is one result. So the first element of the list is the result for ID 1, the next one for ID 2. You know, which one of these you use really depends upon what you want to do with the resulting output. There may very well be good reasons why you want to generate a list of results versus a simple vector of results. It really depends. There's really no right or wrong in this case. I think typically R just says simplify equals true because oftentimes people would like to see it in that manner. But there's no, depending upon where you want to use the output, that defines what you specify as far as the input for that function. Okay, so we've looked at apply, we've looked at L apply, we've looked at T apply. Now we're going to look at another function that doesn't have the apply in the name, but actually is a superset really of that, and that's the aggregate function. And what aggregate does is it really combines calls to T apply and L apply. So what I mean by that is aggregate will split the data into subsets, compute whatever summary statistics you have, and then return the result in a very nice, convenient form. So let's take a look at the arguments for aggregate data frame. Again, very simple set of arguments. We have X, which is the data frame that you want to work on. We have by, which corresponds to the index variable that you want to deal with. And then we have fun, which corresponds to the function. And as Tim had probably talked to you last week, this ... argument just basically says you could pass in other options. This function necessarily wouldn't recognize it, but this was wrapped inside of other functions and you were using it, you might have reasons to pass in other arguments that you've specified. So in order to kind of deal with this, I'm gonna make some more, I'm gonna take the problem data set and I'm going to tweak it a little bit. So the first thing I'm gonna do, I'm gonna create a new R object called prob2, which is simply a copy of prob1. Prob2 now is exactly the same as prob1. Prob1 still exists, but prob2 is simply a copy of it. And I'm going to create some additional variables. In both of these data sets. So for prob1, actually I'm going to create a visit variable for both. In prob1, I'm going to create a visit variable and assign it the value of 1. And in prob2, I'm going to create a visit variable and assign the value of 5. So let's just take a look at prob1. That's prob1. And if we look at prob2, they're exactly the same. The only difference is that the visit value has different variables. And I'm just going to want to combine these later on. The other thing I'm going to do is I'm going to tweak the value of dv in prob2 and make it larger. I'm just going to multiply it by 5. So I'm going to take dv. We did this in the basic functions and basic arguments in chapter 1. We show how we can say make a value larger or smaller, and there's no rhyme or reason to necessarily multiplying by 5 here. I just want to create another variable or another unique set of variables for dv in this data set. And then the last thing I'm going to do before I start to work with it, I'm going to bind rbind. So basically I'm going to take these two data sets and sandwich them one on top of the other. I'm going to bind them by rows, prob1 and prob2. So if we say look at the number of rows in prob1, actually prob2 is 600, and if we look at the number of rows in prob1, it's actually 1200 because prob1 now consists of the data from prob1 and the data from prob2 just binded together, one on top of the other. Now that I have this data set to deal with, I'm going to go ahead and I'm going to use the aggregate function. So let's look and see what this aggregate function is doing here before I run it. So first I'm going to specify the x, or the values to work on. So in this case I'm going to be working on the dv, the column labeled dv. I'm going to be indexing it by visit and ID, and I'm going to be applying the function max. So what's this going to do? Well, this is going to tell me for each ID, for each ID and visit, what's the maximum DV value. Before we do that, let's do this. Let's do something like, just to demonstrate that we have unique visits here. If we did something like unique, you'll notice that we have visits 1 and 5. So we have 2 visits, and we have 2 visits for each individual. So let's recopy this aggregate function down. So again, we're going to operate on the DV column. We're going to aggregate by visit and ID, and the function we're going to use is max. And I happen to write the information out. I wrote the information out to a new R object called max DV by visit. Probably don't want to call it, get your names of R objects to be that, say, complex, but I just, for our purposes in the class today, I wanted everybody to understand exactly what's going to be contained in this. So let's take a look at what that contains. So if I type that back on the screen, let's, what we'll see here is we have argument called groups 1 and 2, and we have an X value. X is the result. So X is the result of applying the function maximum. And so group 1, as you move across the by list, this is so for visit 1, ID 1, the maximum value is 12.66. For visit 5, ID 1, the maximum value is 63.3. And you can kind of go step through each individual. So for each individual, you'll have 2 visits, and you'll have 2 rows. 1 correspond to visit 1, 1 correspond to visit 5. So the nice thing here really is what you end up with is a very nice data frame that you can then use. Maybe you want to do plotting. Maybe you want to plot the average concentration by visit for each individual, or you want to plot, say, the average concentration by visit. This aggregate data frame takes what it gives you back is a nice data frame that you can then use for plotting. And if we wanted to call these something more informative, there are ways to pass the names in, but we also might do something like this. We could say names visit, would spell it right though, visit ID max DV. So now if we do max by visit and we look at the very top of it, now we have a bit more informative names here. So we have visit, ID, and max DV. So now we actually know what these are. And if we're going to use them, say, for plotting or something like that, we actually know exactly what the information contained in each column is. Okay, so that's the aggregate data frame. So again, this is kind of a combination, this is a combination of tapply and lapply, where first it subsets your data by these index variables, and then it applies the function across each of the index variables, and then gives you back the result. So as you can see, we started off today with doing something like table and just looking at, say, groupings of variables, to now we're actually able to, in a relatively concise way, calculate out what the, say, maximum, or we could very easily have calculated, we don't want to count the maximum, we want to calculate the mean here. Now, of course, it's no longer max DV by visit, it's actually mean DV by visit. But you get the idea here. So now instead of looking at the maximum DV, we've calculated the average DV. Okay. So let's cover the last topic here for today, and then we'll either go back and do the exercises or we'll talk a little bit about the homework. So the last thing that you might want to do is subset a data frame using a logical vector. In the case of R, a logical vector contains trues and falses. You can generate a logical vector on the fly, by using, by just simply creating a vector and labeling it as, or creating it as a logical, true or false, contain true or falses. Or oftentimes we do it by testing. But what I mean by that is we will say test a given variable for whether or not something is true or false. So for example, let's do a summary of our prob1 data set again. Okay, so one of the things that you'll notice here in this summary is that one of the nice information that summary provides is it tells you for any given column where there's a continuous variable like weight, in this case weight 3, if there's NAs present or not. So in this case, I know that for weight 3, there's 180 NAs. So when I say, what I mean by testing is we could do something like this. Let's create an object called test NA, and we're going to say, let's test to see what rows in weight 3 are in fact NA. So we're going to use the function called isNA. And so now if we look at test NA, we're just going to take a quick head of that. These are just the first 5 rows of, or 6 rows of NA. And what you see is that it now contains trues and falses. And this doesn't really tell you it contains trues and falses, but we could do something like unique test NA. And now you can be convinced that in fact test NA has values of true and false. Okay, so what will we do with this? Well, and we can also figure out that, let's just say the number of rows in prob1 is 1200, and let's see what the length of test NA is. The length of test NA is also 1200. So for each row of prob1, we have a result in test NA. So what I mean by using using a logical variable for subsetting, we can actually now use this trues and falses to subset the prob1 data set to only rows that have either rows that have NAs for weight 3. So we could do something like this. Let's call it prob3. We'll just call it prob3 NA, so I know what it's going to be. And we'll take prob1, and so now what we're going to do is we're going to apply, not really apply, we're going to take this logical vector and use it to subset the prob1 data set. And so now if we look at prob3, just ahead of it, what you'll notice now is weight 3, in fact, if we were to look at, say, do something like unique, what you'll notice is that all of the rows in prob3 NA have NA for the weight 3 variable. Oftentimes, what we want to do is just the opposite. We want to say we don't really want all the rows with NA. We want to exclude all the rows that have an NA value. So that's very simple. So now that we have a logical vector of trues and falses, that's what test NA is, we can just say not test NA. So we're going to take the opposite. So all the rows where test NA is true. And now if we were to run unique across the prob3 data set, what we'll see is we have no NAs, we have only the weight 3 values. And this could be helpful. Let's just say that you have a data set that you want to do some plotting, and it has missing values for maybe the dependent variable. You might want to, just for plotting purposes, subset that data frame so you only have values that contain something other than NAs or missing values for plotting. So you might subset based upon that logical true-false vector, and then use the new R object for plotting. And if we were to take a look at the number of rows, in prob3, what we see now is we have 1,020 rows in prob3, and in prob3 NA we have 180, and so we're back to our 1,200 rows again. So if you combine these two together, we'll get back our original data set. So as you can see, that logical function is a very nice way, and you're not limited necessarily to testing for NA values. We could have done something like this just to make it, let's just call it test weight. It's not, again, it doesn't mean necessarily anything, but I would say prob1 $ weight greater than 80. And if we do a head-on, again, we should have, and I'll explain to you what's going on here as soon as I do this. We have trues and falses. So what we did is we've generated a logical vector of trues and falses that correspond to true when weight's greater than 80 and false when weight is less than 80. So this is an example of where now you're gonna subset based upon that test weight variable. So let's just call it prob weight, and we could do something like prob1 test weight, and if we were to say summary prob weight, what we'll notice is that for weight, all the values are above 80. So the min's 84, the max is 96. So what we've basically done here is we've subsetted our data, given this logical vector. You can sometimes refer to it as a key. You might want to call it, rather than a logical vector, you might call it a key of your data set. So somebody asked, it's a good question, can aggregate be applied to more than one column at a time? So let's look at the help for that. So we take a look at the help for that. The answer to that would be, yeah, you should be able to apply, X does not necessarily have to be an individual column. You should be able to apply that across, I believe, multiple columns, and I can double check that. In fact, we could test it as we speak. Let's go back to this aggregate item here. So now the question is can you apply the function max across two different columns? So in this case, you have dV and weight. So let's take a look at what the result would be here. So yeah, so now what we've done is we've actually aggregated. Our X now is two variables. It's dV and weight, and we've done it by visit and ID, and we've got the max. So the short answer is yes, you can go ahead and apply aggregate. So now what I have is I have for visit 1, ID 1, what's the average dependent variable, or dV, concentration in this case, and what's the average weight. And then for visit 5, ID 1, what's the average dV and weight. And if you'll remember, I didn't tweak the weights at all. So for these individuals, the weight across visits is going to be the same. I tweaked DV by actually multiplying for visit 5 the weight, the DV value times 5, so they're different, but I didn't do that for the weight variable. Okay, so that pretty much finishes up our class today. So let me just quickly put up the homework here. For Friday's class, what I'd like you to do is do the exercises that we did not cover today. So there's, I believe, exercise 431 and 441. These are internal data sets within R. And then for the homework, also I'd like you to, I've supplied to you a data5.csv data set. I'd like you to read that in, follow the individual bullets, and work through the problems. And then finally, the last bulleted homework item is for an internal R data set. And I didn't actually show you that. So just to give you an idea here, if you need to get at, say, this data set is present in R. So if you do something like data woman, that'll give you the, actually the woman data set's already present. So if you just type women, you'll see the height and weight. You'll see the data set that you want to use. So I think there's the woman data set we use, and we also use the sleep data set, and we use the chick weight data set. These are nice, these are internal R data sets that they provide just for, kind of playing around with functions. And again, if for some reason nice thing is if you mess up one of these data sets, you can't really change it permanently because the data set exists within R. So even if you change it, it'll go back to you can get it back to the normal value again, the normal set of values. Okay, so that's it for class today. We'll meet back again Friday. Hopefully between now and then you'll try the homework and the exercises, and Friday then we'll come back in and answer any questions that might have come out from the homework, and I will supply the answers to the homework as well sometime after class on Friday. Okay, thanks everybody.